Hello class, this is Mrs. Ayodeji with today's video on 14.5 Geometric Properties of Conic Sections and Parabolas. As you're watching the video, write down important vocabulary, formulas, equations, and notes. Feel free to pause or rewind the video as often as you need so you can get a clear understanding of what is occurring in the video. And at the conclusion of watching the video, write a brief summary about what occurred in the video and submit that summary as well as a top question via the online WIS the day before class. All right, let's begin. So we have been discussing and looking at various conic sections in the past videos, and the way that we've been looking at it is only in the implicit form and the parametric form of a description of these curves. And so today's video we're going to focus on the geometric properties of these conic sections. So let's start with circles. We have an general implicit form and a general parametric form of this format, where H and K is the center of the circle and R is a number. And what does that R represent? Well, by the geometric definition of a circle is a set of points in a plane that is a distance of R away from a given point, and that given point is our our center of our circle. And so that's a geometric perspective of circles in combination with the algebraic representation we see up above. Let's go on to ellipse. Now, we know that when we talk about writing the equation of ellipse, we looked at the general implicit form and the parametric form, and each of these forms involve the center HK of the ellipse and these two numbers A and B, where A and B are generally considered to be positive and one is bigger than the other, affects the width and length of the ellipse. But what does A and B and the center H and K, what is that relationship geometrically? So let's take a look. Geometrically, an ellipse is a set of points in a plane for which the sum of the distances to the foci is constant. And so some of you may be asking, where's the foci? We were just talking about the center and the points A and B. Well, there are 2 points that are called the focus points or focal points of the ellipse, and the ellipses can also be defined based off those 2 points instead of just the center and A and B. And those 2 focal points lie on the major axes. So if A is a larger number, then the 2 focal points lie on the x-axis. And if B is a larger number, then the 2 focal points lie on the y-axis, or the vertical axis if the ellipse is not centered at the origin. And most importantly is that there is a constant sum of distances, which represents the length of the major axes. And we'll look at what that means geometrically in a bit. So let's consider this ellipse right here. We know how to draw an ellipse given H and K and A and B, where A is obviously in this picture larger than B, so the major axis is the horizontal axis. But let's say, for example, that I want to make a right triangle such that the length of the hypotenuse is A and the length of one of the legs is B. What would that look like? Okay, so that looks something like this. Here we have and I've centered it at the origin to make life a little bit easier. So this red side length is also the same length as this side length over here. Oh, let me change that to. And so as a result, that means that we have now a right triangle made up of the length of legs of length B, and this other leg, which we haven't labeled yet, and the hypotenuse is length A. So the question is, what is the length of this leg right here, C right here? And we're going to call it C, okay? And really, the distance from the center of the ellipse to C is the location of the focal points. In this case, this is also a length C as well too. So that's where the focal points come from. Given A and B, A is the hypotenuse of a right triangle, B is one of the legs, and the length C will represent the distance from the center of the ellipse to one of the focal points, as we see here. And so the question is, well, how would you determine what C is? Well, if you know what A and B are, you can easily compute C by the Pythagorean theorem. And so now we have a way of describing how to locate the focal point. So in general, the focal point is going to be plus or minus c comma 0 only if the ellipse is centered at the origin. If it's not centered at the origin, then it's going to be h plus c comma k and h minus c comma k. And c can be found by using Pythagorean theorem, where a is the hypotenuse and b is one of the legs. This only maintains itself if a is bigger than b. If b is bigger than a, then we will use this formula to figure out c. And then instead of the focal points being on the horizontal axis, the focal points will be on the vertical axis as well. So moving on, another geometric property is the reflective property of an ellipse. And by definition, a ray that originates at one focus of an ellipse is reflected off the ellipse to the other focus. Okay. And so if I were to shoot X-ray or a ray from a focus to a point on the ellipse, it's going to bounce back off, i.e. reflect, and it's going to pass through the other focus. That's a geometric property. If you want to know why, you can talk about that with your geometry teacher. An application of this is called Lathis Copy, where they basically try and break up a kidney stone. So they place someone in a tank, and they have at one end the shock generator that sends off shock waves to the other focus point, which actually in this case is the location of the kidney stones. And so all these rays are going to be bouncing off here and focus centrally at that kidney to break up the kidney stones. So that's an application, since you guys always ask, when are we going to use this in real life? Well, they use it in medicine. Okay, now let's move on to hyperbolas. Hyperbolas, if you remember the implicit form, they also involve HK and AB. But we have two types of hyperbolas, a horizontal and a vertical hyperbola. So as you can see, they have similar type formats, but geometrically, a hyperbola is a set of points for which the difference of the distances to 2 points is constant. So with an ellipse, it was the sum of the differences is constant, but in this case for hyperbola, it's the differences. And those 2 points are the focus points, or the focal points, or the foci of the hyperbola. So just like in before, where we had an A and a B to be the sides of a right triangle, we're going to do the same thing for a hyperbola, but instead of A being the hypotenuse of the right triangle, A is actually going to be one of the legs of the right triangle. So A and B are actually legs of the right triangle, and C will represent the length of the hypotenuse. So as you can see here, we have our lovely hyperbola rectangle of length 2A and length and height 2B. And then if I were to figure out the length of the hypotenuse of the right triangle with sides length A and B, the sides would be, this would be the length of the hypotenuse. And instead of leaving that in the box, if I were to represent that same length on the horizontal axis on both sides, then this would be length C, and this would be length C as well. And so this is the location of the focus points for the hyperbola, which is C units away from the center of the hyperbola. Okay, and to figure out C, we just use the Pythagorean theorem. Another geometric property of hyperbolas is that it's a reflective property, and if we aim a beam at the far focus behind the hyperbola, it's going to be reflected off the curve and hit the focus in front of the hyperbola. And here's an example of that. As you can see here, we aim the beam here to hit here, but before it actually hits here, it bounces off here to this one as well. So that's a reflective property of hyperbola. It's a little bit different than the reflective properties of ellipse as well. Okay, and then let's talk about the last conic section that we haven't talked about, although we have experience with, parabolas. And with ellipse, we have 2 focus points. In hyperbolas, we have 2 focus points. But with parabolas, we only have 1 focus point. And the definition of a parabola is it's a set of points in the plane for which the distance from a point, i.e. the focus point, is equal to the distance from a fixed line. So that point, which we call the focus point, and the line is called the directrix. Okay, the directrix. So for example, here is a focus point, and then here is a directrix. So every point on this parabola has the same distance from this point to the focus as it does from the point to the perpendicular distance to the line. Okay, and so that's how a parabola is defined. Although in our equation for a parabola, ax squared plus bx plus c, we don't know directly what the location of the focus is or what the direction of the directrix is. So we're going to come up with another expression to represent a parabolic equation. So if xy is on the parabola, that means it's the same distance from the focus point. Let's say the focus point is at the point 0c as it is from the line y equals negative c. Now in this case, we made life easier. We made the focus located on the vertical, the y-axis, and the directrix located horizontally from the x-axis. And so if the distances are the same, then the distance from xy to the focal point can be related using this expression, and the distance from xy to the line, the vertical distance, can be related using this expression. Okay, and so we end up with this is equal to this. So doing some algebraic manipulation, as you can see right here, we end up with x squared being equal to 4cy. And getting y by itself, we get y is equal to 1 over 4c times x squared. So if I know what the location of the focus is, and I know where the directrix is, in other words, there's c away from the vertex of the parabola, then I can represent that relationship using this equation. This equation will change if the focus is not on the horizontal axis. Not on the vertical axis, but on the horizontal axis. It will be x is equal to 1 over 4c y squared. And c, by definition, is the distance between the vertex of the parabola and the focus point, or the focus point, the vertex, the directrix, and a point, and the center, sorry. Okay, and this is a simple case where the vertex of the parabola is at 0, 0, so therefore life is easy. The focus is at 0, c, and the directrix let the line y equals c. Just like other conic sections, parabolas have reflective properties. It says all beams parallel to the axis of symmetry reflect off the parabola to the focus. So if I am actually I have a beam of light that's parallel to the axis of symmetry, and here's, let's say, the axis of symmetry. I can't draw a straight line. Then whenever I shoot it at the parabola, inside the parabola, it's going to bounce off and hit directly at the focus. So every single ray that I do that's parallel is going to bounce off the parabola and hit directly at the focus point. Okay. All right, so that's a lot of information, but the important parts I hope you understood is the relationship between the focal points and the reflective properties of the conic sections. That's it. Thank you.